In the last lecture, I explained the combustion in spark ignition engines. In general, we have identified three different phases in this pre-mix combustion process, combustion in spark ignition engines. Initially, we have this ignition delay period or ignition lag period, and then we have this 10 to 90% of burning phase, that is flame propagation phase. And then the last 10%, that is more or less after burning phase, where you expect the last 10% to burn. And today, initially, I'm going to concentrate on some of the factors that decide the flame speed of spark ignition engines. Flame speed is the most influential parameter that decides the combustion process or the combustion efficiency of an engine. The combustion duration, in other words, will be decided by the flame speed, and the combustion duration, shorter the combustion duration means faster the burning is. That means more closer the process to the ideal process is. Now, as you could recall, the ideal process is instantaneous heat addition. So, without consuming any time, you add heat, and that gives you the maximum thermal efficiency. But practically, you can't do that. It takes time. So, the time taken to add heat will be decided by the flame speed. So, the most influential parameters that decide the flame speed of an engine is turbulence, airflow ratio, the temperature and pressure, compression ratio, the engine output, the engine speed, and the engine size. Now, we are going to look at today, we are going to look at some of these parameters in little detail, how these parameters affect the flame speed and hence the combustion process. Now, if you look at the turbulence first, as we discussed earlier, the turbulence helps to mixing air and fuel together. So that means it helps us to create a homogeneous air-fuel mixture so that we could expect more steady flame propagation during the combustion phase. Accordingly, we could expect fast burning. At the same time, the turbulence helps the flame propagation process itself. Therefore, you could expect fast burning as a result of turbulence. And if you look at the effect of engine speed, as you can see here, as the engine speed is increased, the flame speed will be increased as expected, because as you increase the engine speed, then obviously the turbulence level will be increased due to the increase of swirl, squish and tumble flow. Accordingly, when the turbulence is increased, the flame speed will be increased. And then the other parameter which has a greater influence on the flame speed is the compression ratio. So when you increase the compression ratio, you reduce the clearance volume of the engine. That means you compress the engine, compress the gases more, and that means the density of the air-fuel mixture would be increased, and as a result of that, there will be increase of pressure and temperature, and which reduces the combustion duration. And the higher the compression ratio, accordingly, higher the flame speed will be, and that increase of flame speed would reduce the initial phase of the combustion process. That means it shortens the ignition delay so that you could initiate it close to the top dead center of the piston when it comes through the compression stroke. Therefore, you could produce more energy, more work during the within the engine cycle. So that I will explain again with some pressure volume diagrams later. And then again, as a result of increase of pressure and temperature within the combustion chamber during the combustion, that would speed up the second phase of the combustion, that is the flame propagation period. That also helps to increase the burning rate or reduce the combustion duration as a result of increase of flame speed. And as I just mentioned, the temperature and the pressure during the combustion process has a greater influence on the flame speed. High the pressure and temperature, quick the burning is, high the flame speed is. Then the temperature and the pressure all throughout the engine process inside the cylinder depends on the pressure and temperature at the very beginning of the engine cycle, that is temperature, pressure at the intake. So if the pressure and temperature are high at intake, then again you could expect fast burning or high flame speed. And the other parameter which decide the flame speed or the flame propagation is the air fuel ratio. So the air fuel ratio, if I explain with this diagram, this is the flame speed versus air fuel ratio. As you can see, when the mixture is slightly rich, in this case the air fuel ratio is around 12, you see the highest flame speed. So at the stoichiometry, it's not as high as slightly rich, the flame speed at slightly rich mixtures. So that is also an important parameter. If you go to the richer side of the air fuel ratio, then again you can see the drop of flame speed, because with rich mixtures you can't expect complete combustion. If you do not have complete combustion, then you don't get the expected high amount of energy released out of the system. And again, on the other hand, if you go to the leaner side of the mixture, where more air and less fuel is burnt, then again the energy release, you burn less fuel, that means you release less energy, therefore the flame speed will be less. And on the other hand, the engine output also affect the flame speed, because if you drive the engine with higher output, that means, for example, if you run an engine under wide open throttle conditions, then the pressure, in-cylinder pressure will be high because the throttle is fully open. Then again the pressure temperature within the system is high, that means the flame speed will be high. And on the other hand, if you run it under part load conditions or idle conditions, where the throttle is somewhat closed, then the intake pressure will be less, the pressure during intake will be less, and that means again the combustion, during the combustion the pressure and temperature will be kept at a lower level. Accordingly, the flame speed will be less. And of course, sometimes you may have noticed under idle conditions, sometimes you will feel more vibration of the engine, or because sometimes the engine misses, something like that. So that means the combustion under low pressure conditions is not very steady, therefore there can be some abrupt changes in the engine process or the pressure temperature development within the engine. Accordingly, there can be some instability within the system. So that is one of the problems with internal combustion engines running under low load conditions. So usually under low load conditions, we tend to make the mixture a little more richer, so that the combustion would be enhanced. But again, when you burn rich mixtures, there can be drawbacks or negative effects. Particularly, you will release more unwanted exhaust gases, mostly hydrocarbon, from the tailpipe. So that will not be good for the environment. And the engine size also matters for the flame speed. As you can guess, if the engine size is large, so that means the flame needs more time to travel from one end to the other end, or again from the spark plug to the chamber walls. So more the bore or the stroke is, more the distance the flame need to travel to burn the entire mixture. Therefore, you need more time. You have to leave more time in the engine process for burning to take place. So accordingly, the large engines usually run at lower speeds so that this allowing the necessary time required to combustion to complete. So that is one of the drawbacks with the large size engines, where you need to allow more time for combustion. That means you will have to run the engine at lower speeds. And another very important parameter, a controllable parameter I would say, just like airfoil ratio of course, is the spark time. So the spark timing, as you can see in this diagram, so this is the pressure versus angle diagram, or P theta diagram of the same engine with three different ignition timing. So here the ignition takes place 50 degrees before top dead center. So this is the top dead center. This is 30 degrees before top dead center, and this is 10 degrees before top dead center. As you can see here, you can see the pressure development within the engine is drastically affected by the ignition time. So in this case, 50 degree gives you the best performance, where your pressure is maximum, very large. Accordingly, the area under PV diagram will be large, so that you produce more work. And under 30 degrees, it's little less, and 10 degrees is much less. So the spark timing affect drastically on the work produced by an engine, and work produced by engine is directly proportional to the torque developed by the engine. So if you look at how the torque varies with the spark advance, we use the term spark advance. That means how early that we start burning the gases. How early we start burning the gases is more or less the spark time. So now spark advance. So here the spark advance is 50 degrees, and here the spark advance is 30 degrees, and here the spark advance is 10 degrees. Advance from the top dead center. So how early we start burning the gases. So the spark advance, as you can see here, the torque increases with the increase of spark advance, and after some time it starts coming down. Therefore, there is certain spark timing which produces the maximum torque. So that is called MBT. The spark advance corresponds to maximum brake torque. The spark advance corresponds to the maximum brake torque. So always when you ignite gases, the engines, it is preferred to ignite at this MBT spark timing, where you get the maximum work produced or the torque out from the engine under that particular condition. But again, there are some other constraints to operate engines at MBT. Particularly, there is a phenomena called knocking, undesirable self-ignition of gasoline. Therefore, sometimes we may not be able to operate engines at MBT spark timing all the time. Sometimes we'll have to retard to avoid knocking. I will talk a little more about this as we go on. But again, the spark timing need to be tuned up to give you the maximum timing. Nowadays, that is done using the microprocessor based control system fitted in the engine. Okay, so let's look at the same thing in a slightly different perspective. And so this is the pressure curve against the pressure variation against the crank angle for three different ignition timing 1, 2, and 3. 1 is denoted as the normal curve here, and if you ignite the gases a little earlier, That means if you advance timing from 1, you get timing 2. That means you ignite the gases too early, little earlier than ignition point 1. Number 3 represents the ignition a little later than number 1, so that we call a retarded timing. So retard from ignition point 1, that is the normal curve, and advance from ignition point 1, that is again point 1 is the normal curve. So the advanced timing is over advanced timing is represented by ignition point number 2, and retarded timing is represented by ignition point 3. So this advanced retard is normalized to, or the reference to, ignition point 1. Now what happens is when you ignite gases at the right time, then the pressure will be maximum when the piston just passes the top dead center, so that you could utilize the pressure developed within the piston cylinder system combustion chamber as a result of the motion of the piston to enhance the combustion. So when the piston is at the top dead center, the pressure is usually maximum, and the combustion, 90% of the combustion is completed by that time. So the pressure can be increased. And now if you move on to ignition point 2, what happens is you ignite the gases little earlier, then the pressure started building up early, and then when the piston reaches the top dead center, the pressure is very large, and as a result of that, temperature would be very large. Therefore, sometimes there is a chance that the self-ignition temperature of the air-fuel mixture, the gasoline, would be reached before the flame comes near certain areas. So that is, the flame has to grow from the spark ignition, spark point, and the flame grows and travels from spark plug to the other ends of the combustion chamber. And before the flame reaches the end points or the walls, if the gases near the wall reaches the self-ignition temperature of gasoline, then they start igniting on their own. So that is called auto ignition of the gases, and that creates a lot of problems, and we call knocking. So if you go for over advanced spark timing, of course you can create large pressures, but the problem is the engine would start knocking. So that is an undesirable situation. Therefore, we can't advance timing beyond a certain value. And that is one of the reasons why I said MBT spark timing always we can't achieve in practical engines. So when you try to find MBT, then the knocking would occur. And again, when you go to the retarded side of it, if you delay the spark timing close to the top dead center, if you ignite the gases when the piston is close to the top dead center, then again the maximum pressure will be reached after some time from the top dead center. That means at that time the temperature and the pressure of the cylinder, the combustion chamber, will be less because gases are expanding, piston is going down, so the pressure will be less. Therefore, you won't expect a lot of energy to be produced from that engine. So the spark timing is a very crucial factor. The proper timing has to be achieved. The right timing may not be, the optimum timing may not be practically possible all the time because of this knock. So this diagram shows the spark timing under different speed conditions and torque conditions. So this is the torque and these are different speeds. As you can see here, the MBT spark timing is not unique, not always the same for different loads and different speed conditions. So the MBT changes with load and torque. So different loads and different torques, we don't get different MBT spark timing. And practically, the limit is we consider something like 1% loss line, that is a 1 or 2% loss line, in this case 1%. So that means 1% of, we compromise 1% of brake torque and operate the engine at that point to make sure that the engine doesn't knock. and at the same time the spark timing is highly affected on certain emissions, unwanted emissions, nitrous oxide and hydrocarbon emissions in particular. Therefore, to avoid those situations, usually the engines are run slightly below the MBT timing. That means usually 1 to 2% compromise is quite normal. So, that is what you could see from this diagram. Now, if I talk a little bit about knocking, as we all know, in spark ignition engines, you initiate the combustion process at the spark plug at one point. So, let's say at point A, the spark plug is at point A, and the flame starts to grow in the spherical geometry with time. And as the flame grows, then the temperature and the pressure of the burns on, this white area is the burn gases and this shaded area is the unburned gases. The pressure and the temperature of this area or this volume is increased. As a result of that, it will compress the unburned gases to small volume, as we discussed in the previous lecture, like this. And if this when the flame reaches, the flame travels towards the N gases, we call N gases, that is gases far away from the ignition point. When the flame reaches the N gases, or before the flame reaches the N gases, the auto ignition temperature of this gasoline is reached, then they will start burning on their own, so that the pressure wave will be generated in the other side. So this is the the propagation of the proper flame, and this is the propagation of the flame due to auto ignition. As a result of that, very undesirable pressure fluctuation would take place, as you can see here, the pulsating pressure waves, and that will create a noise called knocking, and that can easily damage the structural component of the engine. So this is a pictorial representation of it. As the burn gases come and reach, so as the burn gases moves, or the flame moves, then certain areas in the unburned zone, at the N gases in particular, could start igniting on their own. So we have to control auto ignition. One way of controlling auto ignition is using retarding spark ignition timing, or else we can use other techniques. There are a few other techniques also where you could reduce temperature by mixing with exhaust gases. So we call exhaust gas recirculation and so on. Usually this auto ignition happens due to two phenomena. One is called surface ignition, that is gases near the combustion chamber walls, particularly heated areas of the combustion chamber walls, like piston crown and exhaust valves and things like that. So the temperature, the heat transfer from the walls to gases would increase the temperature, and as a result of that, those gases would reach auto ignition temperature and start igniting on their own. And the other mechanism is the self ignition. As a result of the high pressure and temperature within the unburned gases, there can be spontaneous auto ignition within the unburned gases. We use parameter called octane number of a fuel to characterize the fuel based on the tendency of knocking. So higher the octane number, the less the tendency for auto ignition. In other words, if the octane number is less, that fuel is more prone for auto ignition. So this octane number is a kind of a value that is obtained with reference to a certain standard fuel. Standard fuel that we use for obtaining octane number is isooctane and N-heptane. So isooctane, that is C8H18, is considered as octane 100. So octane number of isooctane is considered as 100. And N-heptane we consider the octane number is 0. So any fuel could have an octane number in between 0 and 100, and I'm pretty sure you are familiar with octane 90 and 95 fuel that we usually have. In fact, 92 and 95 fuel that we have in the market in Sri Lanka. So, so this octane number, if you get octane 100 fuel, that is perfectly C8H18 isooctane, and if it is octane number octane 95, that means 95% is isooctane and 5% is in heptane. So it is 95 fuel. So so usually this value is experimentally found the octane number using two techniques. One technique is called motor octane number, and the other one is called research octane number. And of course, there are standard test procedures to do this. And if you have done any training at Petroleum Corporation, you would have seen how this octane number is practically found. And of course, based on these two experimental values, motor octane number and the research octane number, the practical octane number that we see in fuel is obtained as an average of this. So in fact, what we see here is the auto ignition anti-knock index, that is motor octane number plus research octane number divided by 2, and that is what you get from the pump. And of course, the self-ignition capabilities, in addition to the octane number, the self-ignition of spark ignition combustion process in an engine depends on many other parameters also. The combustion chamber geometry, the turbulence swell, temperature and pressure, air-fuel ratio, ignition timing, etc. And of course, higher the flame speed, quicker the flame grows and completely burn the mixture, so that it is less prone for auto ignition. So before gases auto ignite, before this heat transfer takes place from walls to gases, for example, if the flame goes and burns everything, then the job is done. So higher the flame speed, lesser the tendency for knocking. Therefore, we call system the fuels with high octane number would have high flame speeds. And in practical engines, of course, mostly modern engines fitted with microprocessor based control systems are fitted with a feedback system to decide the spark timing or knock limited spark timing. That is, as I said earlier, about a bit of a small compromise of MBT spark timing. So there is a knock sensor fitted to the engine, and that monitors whether the engine experience some kind of vibration, knocking kind of thing, and then the spark advance is set based on the signal that you get from knock sensor. So if the knock sensor reads some knocking or vibration, for example, and then the spark is retarded in order to make sure that knocking would not take place under that condition. Because as I said earlier, the spark timing is highly dependent on the MBT spark timing, I would say, highly dependent on the load condition as well as the speed condition of the operation of the engine. So you can't fix the spark timing to a one particular point all the time, because practically automobile engines operate under various different speed and load conditions. Therefore, as the load and speed changes, you'll have to change the spark timing to get the maximum output or the maximum torque. Accordingly, a feedback system using knock sensor is used to do this estimation correctly. And of course, this the octane number is a fuel property, and the fuels with longer chains of hydrocarbon molecules have higher octane numbers. I'm not going to go into details of this of chemistry of these. Certain fuels with what I want to tell you is basically the atomic structure or the molecular structure of a fuel decides the tendency for knocking or tendency for auto ignition, accordingly the octane number of the fuel. And again, fuels like alcohol or methanol, ethanol, naturally the flame speed is higher. Accordingly, the burning rate is high. Therefore, the octane number is high. So, if you run an engine, a gasoline engine with ethanol, you could advance the spark to get more power out from the engine. And of course, there are several additives that are added to petrol to increase the octane number. There are so many different chemicals used. I'm not going to go into all these details, but just for your information, if you are interested, you can search this in the internet and get more information. So usually the fuel manufacturers, they add certain additives, as you can see here, to increase the octane number.